right. So, you know, in the first 3 lectures, we talked about higher form symmetries, higher group symmetries, and I illustrated them in using very simple weakly coupled examples, sometimes free examples. And it's, of course, very nice and a good starting point to understand symmetries in simple weakly coupled examples. But the primary motivation for developing this technology is so that we can apply it to examples where we can't actually calculate what's going on. And we have some kind of strong coupling problem. We don't know how to solve for the dynamics exactly, and we use symmetry as a tool to learn about what's going on. And so a primary motivation for everything that I've said so far has been kind of building up to trying to understand better the dynamics and the phases of gauge theories, non-abelian gauge theories, strongly coupled gauge theories in any dimension, but specifically in 4 dimensions. So I'm going to stick in 4 dimensions as I've done throughout. And of course, one hope is to make contact with real QCD. Remember, real QCD is an SU3 gauge theory plus quarks. We'll get there by the end of the lecture, but let's start. Let's start with pure SUN Yang-Mills theory, just to get situated. No quarks, no matter. So remember that we had a long discussion about Maxwell theory and its one-form symmetries. It had a U1 magnetic, it had a U1 electric. And essentially the reason it had those is because it didn't have any charges. The moment we added charges, we broke these symmetries down. For example, when we added electric charges in multiples of n, then the electric one-form symmetry was broken to Zn. If we add fundamental electric charges, the electric one-form symmetry is completely broken. And that was kind of in one-to-one correspondence with the statement that Wilson lines whose charges are multiples of n can end on charged local operators, right? So what I would now like to do is to transport this understanding to sketch a little bit what are the higher symmetries of SUN Yang-Mills theories and discuss some of their properties. Okay. So the key difference between abelian gauge theory and Yang-Mills theory, which you learned from day 1 about Yang-Mills theories, is that the gluons carry color charge, right? The gluons are themselves in a non-trivial representation of the gauge group, the adjoint representation, and therefore, without adding any matter fields, the gluons can screen certain types of Wilson lines. And in particular, they can screen any Wilson line that is in the product of adjoint representations of the gauge group, right? So if you take a Wilson line, remember, in a non-abelian gauge theory, a Wilson line, or Wilson loop, is labeled by a representation of the gauge group, so he'll be a representation of SUN. And, this is a trace in the representation R of some path-ordered exponential, something like this. This is the holonomy of the SUN gauge field in the representation R. And if, for example, R is the adjoint representation itself, then you can end this line by simply sticking in a field that transforms in the adjoint. For example, you can stick in the adjoint valued non-abelian Yang-Mills field strength. Let me call this little f to keep going with the notation that I've been using. All right? So at the very least, we learn that all representations that can be screened by adjoints cannot possibly be protected by a one-form symmetry. Well, what are the properties of such representations? Well, the adjoint representation in Yang-Mills theory is described by a Young tableau with n boxes. And if you keep taking tensor products with itself, you get more Young tableau with n boxes. And so the representations that can be screened are precisely those for which the Young tableau has a number of boxes that is a multiple of n. And this is closely related to the transformation properties under the center of the gauge group. Okay, so let me remind you that, well, even in Yang-Mills theory, I tried to say that you should think, even in abelian gauge theory, I encourage you to think about the electric one-form symmetry as being associated with the center of the gauge group, and the same will be true here. So let's see how that comes about. The center of SUN is Zn. Right. And every single SUN representation R, in particular, transforms under the Zn center, so it carries a mod n charge, from 0 to n minus 1, if you wish, that characterizes its charge under the center. And this charge is sometimes, this center charge, the Zn charge, is sometimes called the anality. This is a generalization of triality in SU3 gauge theory. All right, and this is an integer between 0 and n minus 1. So the representations that can be screened by adjoints are precisely those that have vanishing anality. And the reason for that is that you can prove that the anality of a representation is precisely the number of boxes in the Young tableau mod n. All right? So just to remind you, the adjoint looks something like that. Right? It has, the adjoint is, roughly speaking, a fundamental times an anti-fundamental minus the trace. And there are n boxes here. So this has anality 0. The fundamental representation just has a single box. So the fundamental representation always has anality 1. Right? Yeah, I don't even know if I want to introduce a notation for that. Anyway. Very good. Okay, so this is a purely algebraic fact about SUN representations. What does it have to do with the one-form symmetry? Well, so we already decided that all representations of zero anality can be screened. So let's look at the kind of converse of that statement. Let's take some representation of R that has non-trivial anality. For example, you could take the fundamental. If n is big enough, you can take the symmetric, the antisymmetric. They'll all have non-trivial anality. And see what we can say about it. Well, because the gluons themselves don't carry any anality, nothing that you do here, nothing that you insert on the line, can change the anality on the line. So if you take the fundamental representation, you can never have a picture like this, where the line ends on the fundamental representation. You can stick, for example, you can stick the field strength operator somewhere in the middle of the line. That's fine. You can take a piece of the line, end it here, continue it there. But this f doesn't change the anality on the line, right? It would just kind of give a trivial contribution. So that means that this line, this fundamental Wilson line, somehow carries a Zn valued flux that is conserved even if you insert and collide it with adjoint valued gluon fields. All right, and this somehow gives rise to the idea, right? Remember I told you that you should think of one-form symmetries as a kind of flux conservation symmetry. So this gives rise to the idea that there's a Zn valued discrete flux in these theories that is actually conserved, right? So the idea, the suggestion, is that this Zn center is actually a manifestation of a Zn one-form symmetry that protects the Wilson lines, and the charge of a Wilson line is precisely its transformation under the center of SUN. Very good. Now, this intuitive argument is correct, just like the intuitive argument about ending lines in abelian gauge theory gave the correct answer. Now that you believe that there ought to be such a symmetry, you can try and go ahead and do all the things that we did with the symmetry in the abelian case. For example, you can try to construct explicitly the topological two-dimensional charge surfaces, the Gaussian flux surfaces that measure this Zn flux. I'm not going to do that explicitly, but I'm going to tell you roughly what they look like. So these things are basically kind of Zn vortex defects in 4 dimensions. They're sometimes called Gukov-Witten defects. So they're surface operators that have the property that, right, a surface operator in 4-dimensional spacetime in R4 is the same. If you focus on a spatial slice, it's the same as a string, as a line defect in R3. If you forget about the time dimension, right? And then as you go around a string, this is a codimension 2 defect. So as you go around the string, you can impose Zn monodromy for the Zn holonomy for the gauge fields. So this, if you wish, this is a kind of twist defect or vortex defect. And if you, in principle, you can pick the holonomy any way you like. If you pick it to be exactly valued in the center of SUN, then you get a topological defect. So this is one way you can engineer these Gukov-Witten defects, and there are other ways as well. There's no kind of super simple formula like we wrote down in Maxwell theory. There's no simple formula that's just the integral of star of f, because now f is non-abelian, and if you do that, you get something that's kind of not gauge invariant. And there's a whole story about how you might try to fix it, but that's not what people typically do. The other thing that we learned is that you should be able to couple, once you have such a discrete Zn one-form symmetry, you should be able to couple it to background fields. And remember, I told you in the context of Maxwell theory that the appropriate background fields they're still 2-form background fields, but they are now discrete background gauge fields, so they're kind of flat connections. And you can associate them with elements of cohomology with coefficients in Zn. So these were in 1-to-1 correspondence with the kind of holonomies of the B field in the conventional normalization where the holonomy was an integer multiple of 2 pi over n. So let me maybe not write that. There's a nice trick to take such a field and explicitly couple it to the Young-Mills Lagrangian. That trick involves the realization that if you embed SUN in UN, then the central Zn is shared between the U1 and the SUN. And therefore, you can basically repeat the story of the one-form symmetries for the U1 and write a coupling for this B to the Young-Mills Lagrangian. I'm not going to do that explicitly, but I just wanted to mention it. It's not going to be necessary for what I'm going to tell you next. Of course, if you actually want to, apply this to a real problem, you need to learn about these things. All right, so that's the second point of view. The next comment I want to make is, here I've been discussing the Wilson lines, right? And so you should think of this flux conservation symmetry, this one-form symmetry, as an electric flux conservation symmetry. It's a center symmetry. Yeah, I should say that people call this center symmetry. This is a very old name that long predates the idea of one-form symmetries, and I'll tell you in a second, roughly speaking, where it first cropped up. So depending on your worldview, you either like this name or you don't like this name, but it is standard.
Question? So for the Gukov-Witten defect, there is no singularity on the line, is there? On the surface?
There is. It's a kind of, the vortex defect. You prescribe the holonomy of as you approach the defect, you prescribe the holonomy of the gauge field going around the defect. So the field is not blowing up. It's a kind of Dirichlet boundary condition, and you're not, there's no singularity in the field as you approach the line, but there is monodromy, and that means that if you integrate across the line, there's a kind of discrete flux, and so there's some kind of singularity. I mean, you always need to kind of regularize this operator.
Some kind of solenoid in
Yeah, It's a discrete kind of Zn valued solenoid.
And outside the field is just zero.
Completely flat.
Exactly. One way to regularize this is to drill a small tube around this. Then you don't need to put any non-zero field, and you just put the flat connection around.
Yeah.
Sorry, I think I missed. This is a surface, or this is a tube.
Well, remember that the one-form symmetry topological defects are always surfaces in 4 dimensions. So this is a surface in space-time. And then what I was focusing on here is its spatial profile at a fixed time slice. Right. So when the spatial part is just a line or a curve, and the defect has some prescribed Zn twist around it. Why is that so? Well, after all, this thing is supposed to measure the anality of a Wilson line, and if you wrap a small Wilson line around this twist defect, right, that's exactly what it'll do. So if you link a Wilson line in a representation R with this defect, it'll spit out the exponentiated Zn charge, the sort of nth root of unity times the line. That's what it's designed to do. All right. Let me make a comment about.
Sorry, it's again related to this defect. Is the analogy in Maxwell? Is there an analogy of Maxwell with a different interpretation of the star change?
That analogy is not straightforward, but in Maxwell theory you can work it out. In Maxwell theory you can prove you can take the defect I wrote down for you, and you can prove that it has the effect of generating this monodromy around the defect. So that's an easy exercise in equations of motion. You can try it. Yeah. Let me say something about magnetic symmetries, right? So in Maxwell theory, we also had the U1 magnetic, which was in particular unbroken when we added electric matter. In non-abelian gauge theories, well, in both abelian and non-abelian gauge theories, you probably know that the existence of stable monopoles is related to the topology of the gauge group. So in particular, the reason we have non-trivial Dirac monopoles in U1 gauge theory is because U1 is not simply connected, and pi 1 of U1 gives you the classification of monopoles. The same is true in non-abelian gauge theory. If you have a gauge group that's not simply connected, for example, like SO3 or PSUN, then you can have stable monopoles, but SUN is simply connected. All right, pi 1 of SUN is trivial, and therefore there are no magnetic one-form symmetries in this theory. So that means that there are no stable 't Hooft lines that are protected by such a symmetry. So I won't discuss that anymore. All right, very good. So let me tell you a little bit about the context in which center symmetry first appeared, which is also one of the kind of prime applications of one-form symmetry in Yang-Mills theory. So remember that we're trying to use one-form symmetries, among other things, to classify different phases of gauge theory. We saw that the Higgs phase, for example, was a phase in which the U1 magnetic was unbroken, and if you apply electric magnetic duality to that, you can say that the confining phase is a phase where the U1 electric is unbroken. And this is the context in which this Zn one-form center symmetry kind of makes its most prominent appearance. And the thing that people were thinking about is what happens when you take SUN, Yang-Mills theory, and you study it as a function of temperature. You heat it up. Right, so if you're very low temperature, you're in the vacuum, you're in 4 dimensions, and the theory is supposed to confine. I'll say a lot about that in a second. And then the question was, what happens when you heat the system up? And the statement that was found, let me write it down and then I'll say a lot about it, is that, so if you put Yang-Mills theory at temperature T, then you find that at low temperature, the Zn is unbroken, and at high temperature, it's spontaneously broken. So this fact means that, so once you believe this fact, which I haven't explained to you, you can deduce unambiguously that there is a sharp non-analytic finite temperature phase transition. So you go from low T to high T, and this is the deconfinement transition, as we'll see in a second. And this is indeed what is observed, for example, in lattice gauge theory. You can take Yang-Mills theory and you can put it at finite temperature on the lattice and you can simulate it. And you indeed see this sharp phase transition. This phase transition is generically first order, except in the case of SU2, where it's believed to be second order.
So the Yang-Mills theory have no matter,
Just pure Yang-Mills theory. Yeah. And the absence of matter is actually crucial. So we'll soon add matter, and then the story will change. Very good.
So it's first order in 3 plus 1D.
Well, I mean, so we're studying the theory on R3 times S1 beta, right? So it's first order, you know, if you think of this as an effective three-dimensional theory, it's first order in that theory, if you wish.
You will say a little bit more?
Yeah, say a lot more.
Are you going to say plus 1D gauge theory?
I think the story there is believed to be very similar. Yeah. I don't remember if the exact. I think even the orders of the transition are believed to be the same. I think for n, so I think only n equals 2 is believed to be special in second order, both in 2 plus 1D and 3 plus 1D. And for n equals 3 or higher, it's believed to be first order. Although I understand that actually there's some kind of confusion on the lattice about exactly whether or not SU2 is second order, because even on very, very large lattices, they don't see any evidence of kind of critical behavior. So maybe it's very weakly first order. Most people assume it's second order.
Is there a candidate for the CFT or?
Yeah, it's supposed to just be Ising. Yeah. I mean, if you know that in SU2 gauge theory, the relevant symmetry is Z2, and if you know that it's second order, then generically that should be Ising. But nobody has measured the critical exponent because of what I just said. Nobody has gotten to the critical regime. So in fact, it's not really known.
All right.
Very good. So let me say a little bit more, as I was instructed to. So let's talk about the low temperature phase, right, where the one-form symmetry is unbroken. Well, let's remember by analogy with the abelian-Higgs model what an unbroken one-form symmetry is supposed to imply. In the abelian-Higgs model, we had an unbroken U1 magnetic, and that implied the existence of finite tension magnetic flux tubes, right, which gave an area law decay for the 't Hooft loop, and which gave kind of linear confinement of monopoles in the Higgs phase. And as I told you at the end of that lecture that if you think about this in electric magnetic reverse terms, you get the statement that if you have an unbroken electric one-form symmetry, like this Zn, then you should expect similar statements. So at the very least, you should expect some kind of decay of the Wilson loop fast enough to have zero VEF, faster than perimeter. And maybe you know, you should even expect the existence of finite tension confining strings that actually give you area law decay and linear confinement for electric charges. So this is indeed what happens. Right. So in Yang-Mills theory at low temperature, and in particular at zero temperature, if we talk about zero temperature for a second, that's just a flat R4 case. Yang-Mills theory is believed to do the following three things, which are closely related but not identical. they're usually conflated. It first of all generates a mass gap. So the vacuum is completely trivial. There's no BF theory, no TQFT, not even an non-trivial invertible TQFT, nothing, just boring. Proving this, $1 million. The downside is that you have to prove it at the level of rigor that most people can't even wrap their head around. So that's what makes it hard.
If you do lattice Yang-Mills theory, this seems trivial in the strong coupling limit.
Well, but the strong coupling limit is not the one that's appropriate for the continuum case. Well, that was, Wilson did that before I was born. So beautiful as it is, we would like to do better. Right. The second thing that happens is indeed that the Z and one form symmetry is unbroken. And all the Wilson loops of non-trivial anality, for example, the fundamental Wilson loops, decay to 0, have 0 of f at long distances. Now, as I emphasized yesterday, all this means is that you need to have the quark-anti-quark potential rise at infinity. And it doesn't tell you how fast it rises. The third thing that's supposed to happen in Yang-Mills theory, which is also known from lattice simulations, it's known from the strong coupling limit, but at weak coupling it's known from numerical simulations. The third thing that is believed to happen is the formation of finite tension strings, confining strings, which in particular give you area law and linear confinement with finite string tension. So this is logically independent from this, and it's stronger than this. But all three things are true. And I emphasize that I think the only evidence we have directly in the physical regime, the continuum limit, small n, no supersymmetry, is from the lattice. I don't think. Yeah.
Does the second and third statement require the first one to be true? If it's not, if it's gapless, is it meaningful to ask whether it's broken or unbroken, or?
Yeah.
Because if it's conformal, if it breaks, you have a
For example,
tension, which
we had a discussion an interesting discussion, perhaps unresolved, in QED yesterday, which is gapless and presumably has an unbroken one-form symmetry.
Well, here it's UV complete, so if it's gapless, it would be like a CFT in the IR. No? Doesn't matter.
It may or may not be a CFT.
Maybe my question is whether the finite tension is compatible with conformal invariant. Because
No,
it's a
for sure
scale.
not. It's a scale. Yeah, but yeah. So if the thing flows to a CFT in the interval, then for sure this is not true. Yes. I believe that these three statements are not independent, but to my knowledge, nobody has proved a theorem relating. So I think that's an interesting open question.
Okay.
Yeah.
Maybe a third statement follows from the first two.
That's right. So of course, this, not the first two, just this one. This implies that.
No. The first two statements imply the third statement.
Where in which order the numbers?
No. Mass gap plus unbroken, does it apply area law?
No, I don't know that. Nobody knows that. There's no proof. That's so clearly this implies that, and I think it's sensible to hypothesize that these two imply that, which is what you're suggesting. There's no argument to this effect, though.
And with like gap phases with the one form symmetry.
Yeah. So I think a reasonable conjecture is that gapped phases with unbroken ZN1 form symmetry have area law. We don't know a counterexample to that, but there's no proof. I think that would be a kind of potentially doable step on this rather hard problem. The assumption of the gap is crucial because yesterday I gave counterexamples in the gapless case. Yeah. as I said then, I think in some extremely dumb sense, there's some intuition that maybe area law is the sort of standard exponential decay that you would expect for correlation functions in a gapped phase, right? Analogous to the exponential decay of local correlations. Yeah, but we're not, that seems like something that maybe one can understand. Okay, very good. Now, what happens when we heat the system up? Well, when we heat the system up, then in the very early days of QCD, people like Polyakov and Susskind tried to understand the finite temperature phase transition by considering an order parameter that was a Wilson loop wrapped on the thermal circle. Right, if you take the thermal circle, it has non-trivial, right? It's topologically non-trivial, so if you wind a Wilson loop on it, that Wilson loop is actually charged under the one-form symmetry. Part of the reason that is a simpler setup is that from that point of view, the one-form symmetry looks like a zero-form symmetry in 3 dimensions, so it looked more familiar to them. And this is what they called center symmetry. Center symmetry was the Zn action on this wrapped Wilson loop on the thermal circle, which looked like the normal Zn symmetry. And then the confusion in those days was that you have this symmetry when you put the theory on a circle, and then it disappears when you go to R4. So that was kind of confusing. And now we understand that the symmetry isn't gone in R4, it just becomes a one-form symmetry. And so you have to understand it in those terms. And what happens, right, is that at very low temperatures, this Wilson loop has 0 expectation value. And if you compute it in the very high temperature limit, the very high temperature limit is more or less tractable. It's not quite weakly coupled, but it's almost weakly coupled because of asymptotic freedom. Then you can show that the Wilson loop expectation value is actually non-zero in the high temperature limit. So we get a temperature. All right.
Can you be a bit more precise? When you reduce the theory on the circle, so you're saying that for Wilson loops which are wrapped around the circle, okay, for those things, one form becomes just a zero-form symmetry.
Yeah, let me draw a picture. But
what happens? We still have Wilson loops which are not wrapped.
Correct. So you now have 2 types of Wilson. So the 4D one-form symmetry splits into a 3D one-form symmetry and a 3D zero-form symmetry. So the 3D zero-form symmetry is the one that acts on loops wrapped around this circle. Remember that the surface is a 2-dimensional surface. The topological operators live on 2 surfaces, and they link the Wilson loops. So if you wrap the Wilson loop around the circle, in order to link it, you have to put the 2 surfaces directly in 3 dimensions, where it's codimension 1. So there it looks like a zero-form symmetry. And indeed, this looks like a point operator in 3 dimensions. But if you put the Wilson loop in 3 dimensions, right? Then in order to link it non-trivially, you need to take one leg of this surface to be on the circle, and then you get a codimension 2 operator in 3 dimensions, which is a line linking the Wilson line, and that's the one-form symmetry.
The reason why I'm asking is that I'm trying to understand how this matches up with your suggestion that for n equal 2, the phase transition is believed to be the Ising universality.
Yeah, it's for this symmetry, which is a standard zero-form symmetry from the 3D point of view.
But this Zn1,
This is unbroken.
Well, it's unbroken, but it's supposed to be realized in the CFT. And
No. The Zn1 actually, it turns out to only act on the kind of zero mode sector, like the very low energy sector of the theory. It doesn't act in an interesting way on this loop, which is dominating the thermal transition. There's a kind of decoupling that happens. The thermal transition is driven by kind of electric degrees of freedom on this circle, and then this Zn1 is basically the one-form symmetry of the 3-dimensional Yang-Mills theory that corresponds to the zero modes on the circle, and they basically decouple for most intents and purposes. There's like 40 years worth of fine print in this statement, but it's roughly true. Okay.
Z1 and is unbroken. Nothing happened in n equal to 2. Nothing interesting.
Well, so Zn1, as I said, so basically what this Zn1 acts on is more or less a 3-dimensional Yang-Mills theory in R3, which is itself confining. So this three-dimensional gauge theory being confining corresponds to its one-form symmetry being unbroken. Yes. Very good. Okay, so this is the kind of prototypical and probably most important application of one-form symmetry to diagnose the deconfinement transition in pure Yang-Mills theory. Now, you can do lots of other things with one-form symmetries in Yang-Mills theory, and you can do lots of things in Yang-Mills theories with matter that doesn't destroy the one-form symmetry. So we're going to talk about adding matter very soon that does destroy the one-form symmetry, because that's what happens in real QCD. But you can consider interesting and fun examples of matter like quarks in the adjoint representation, or Higgs fields in the adjoint representation, both of which are very natural in supersymmetric theories. And then you don't destroy this ZN center symmetry, and you can try to use it to say something about the dynamics of these theories, and you can match anomalies, and you can look for phase transitions. So that's a nice and beautiful story. But in the remaining, however much time I have left, hour or so, I'm going to try to switch gears a little bit and talk about QCD with fundamental quarks. Are there any more questions about this?
So maybe a stupid question. So here you mean the low temperature, the zero form symmetry is unbroken, and the high temperature, the zero symmetry is low?
Correct. So at low temperatures, neither symmetry is broken, and at high temperatures, the zero form part.
I'm just confused because you know in the conventional phase diagram, the low temperature is your
That's an excellent question.
order of the phase.
Right. You're complaining about the fact that usually, when we heat up a system at high temperatures, the symmetry is restored, and here it's backwards. That's completely correct. This is a feature of one-form symmetries. So this is what you're saying is generically true, and it's generically true for zero-form symmetries. But generically, the opposite is true for one-form symmetries, precisely because they're typically confined at low temperatures and typically deconfined at high temperatures. So anyone who believes that there has to be a kind of universal theorem that all symmetries are restored at high temperatures, this is a counterexample. There has to be some kind of caveat. Right, and there was an interesting discussion yesterday about how those two statements are actually in conflict with each other when you have a two group, so it gets even more confusing.
Yeah. So suppose you have a matter with a very heavy mass. So then at a very high temperature beyond the mass scale, then all the symmetry will be broken.
That's right.
So this is the assumption that somehow the mass is the matter is always not there. But this
Right. Well, if you wish, it's a question about how heavy the matter is, right? So indeed, if you add matter, and I'll do that in a second, if you add quarks, for example, they break the one-form symmetry. If the quarks are very, very heavy, for example, imagine that the quarks are super heavy, like the top quark or something. It's much heavier than lambda QCD. Then this deconfinement, this more or less sharp deconfinement transition will set in kind of long before you activate those degrees of freedom. And so that means that if the mass is sufficiently heavy, you basically get a very high quality emergent one-form symmetry. It's not exact, but it's kind of exponentially good. If the quark mass is kind of comparable to lambda QCD, then the symmetry is badly broken. In fact, I'll say something about that in just a second.
Like finite temperature theory in real time, Schwinger careless or something. Is there another parameter?
I don't know.
I don't even know. Well, you must know better than I do. But I don't even know what is known about the real-time behavior of this deconfinement transition. Right. The statement that it was Ising is only for the static part of the theory. So it doesn't need to be Ising, and it doesn't even need to be relativistic. I think maybe people believe it has non-trivial Z. I don't know. All right. So let's go back to the thing I started with, which is QCD. QCD is one example of SUN gauge theory. It's SU3 gauge theory. And we can take a bunch of fundamental quarks. In principle, we could take NF fundamental Dirac quarks. And for the purposes of the discussion, let's take NF to be 3. And the reason we take NF to be 3 in this discussion is roughly because of the conversation we just had. The other 3 quarks are heavy above the QCD scale, and so they don't participate in a lot of the strong coupling dynamics, or at least they do it in a very different way. So this is QCD with 3 light quarks, right, up, down, and strange. And let's discuss a little bit about how this changes the story. Right, so each quark, of course, I mean, the Lagrangian is the standard Yang-Mills Lagrangian. Then each quark is described by, each flavor of quark is described by the sort of standard Dirac Lagrangian coupled to the covariant derivative for the Yang-Mills fields, and then in principle it can also be a mass for each quark flavor. All right. Now, the quarks are in the fundamental representation of the gauge group. So that means by everything that we've discussed, they can end the fundamental Wilson line. In fact, that's how you build gauge invariant quark operators, right? A quark operator by itself is not gauge invariant. So if you want to make it gauge invariant, you have to stick a Wilson line at the end, and then you get this kind of gadget. And that in particular means that the Wilson line in the fundamental representation can end. All right. So what does this mean? This means that QCD with fundamental quarks has no one-form symmetry. And eventually, if you're interested in actual QCD, you're going to have to come to terms with this annoying fact. One-form symmetry will only get you so far. What does this mean? Well, it means the Wilson line can end. It also means that, for example, if you take a QCD string, or a Yang-Mills string that's supposed to be created by a fundamental Wilson line, this string is no longer stable. In pure Yang-Mills theory, the string was protected by a kind of this flux conservation symmetry, and now the flux can be broken by a quark-antiquark pair, so the string can decay. How fast it decays depends a little bit on how heavy the quark is. If the quarks are light, they decay pretty fast. If the quarks are heavy, it's kind of exponentially slow. That's related to the emergence of a one-form symmetry at heavy masses. Very good. Now, as you all know, even in QCD with quarks, even though there's no one-form symmetry, there's what used to be confinement, called confinement in the old days before we started having sharper notions of what confinement is, which today is typically called color screening or color neutrality, right? So QCD is strongly coupled, and so the quarks and the gluons form color neutral bound states. So that's the sense in which there's no unbound color. Color is quote unquote confined, but there's no confinement in the sense of unbroken one-form symmetry, stable strings, etc. Those don't exist. Very good.
Is there any way I could formulate a broken word identity for the one-form symmetry, or is not smart to think about?
To the extent that people have tried it all, I think they've tried in the case when the quark mass is very large. I think that when the quarks are light, like the physical quark masses are very light or comparable to lambda QCD, I think there's no real hope that that's true. And in particular, you can go ask the lattice gauge theorists what this theory does at finite temperature and try to look for the analog of this deconfinement phase transition. And if you do that, you will find no phase transition. So real QCD with physical quark masses as a function of temperature has some kind of crossover, but it doesn't have a sharp thermodynamic phase transition. So in QCD, the high temperature phase, which is kind of the quark gluon plasma of QCD, and the low temperature phase, which is the kind of hadronic one with baryons and mesons and color neutrality, those two phases look extremely different, but you should think of them as the analog of kind of steam and water in the liquid vapor transition. They're not Landau different phases. They're somehow part of the same phase, even though they quantitatively look very different. All right.
Are you going to discuss the stuff for massless quarks?
That's a well-known story. So I will discuss something else. The thing I want to discuss in the remainder of the lecture is an interesting consequence of the absence of a one-form symmetry in QCD, which is different from the absence of a finite temperature phase transition. Right. So if we stay away from the massless point that you were just asking about, if we keep the quark masses non-zero, then QCD with quarks is also a gap theory. Right? The vacuum is also gapped and trivial. But remember, yesterday we spent some time discussing the fact that Higgsing is also a way to make a theory gapped and trivial. So yesterday we Higgsed an abelian gauge theory down, and depending on what Higgs field we chose, we either got a TQFT or we got a trivially gapped theory. But you can do the same thing in non-abelian gauge theories. And in particular, you can do it in SU3 gauge theory. So adding fundamental quarks, at least adding fundamental massive quarks, is a way of getting a theory without a one-form symmetry that is trivially gapped in the infrared. But another way of doing that is to just take SU3 and add fundamental Higgs fields. Right? So let's imagine we add a Higgs field in the fundamental representation of SU3. Then if this Higgs field gets a VEV, we can at the very least break SU3 down to SU2. And then we can add another Higgs field. We'll do it again. So we add two Higgs fields, and then we can break SU2 completely. And so by adding two fundamental Higgs fields, we can break SU3 down to nothing, and we can get a completely gapped boring phase. So then an interesting question presents itself. This is an interesting gap. Sorry, this is I was going to say boring gapped phase in the infrared, and this is a boring gapped phase in the infrared. And on top of that, we have no notion of symmetry that we can use to characterize the phases. So if you kind of believe very strongly in a Landau paradigm-driven world, where every phase transition has to be explained by a symmetry breaking, and any two phases don't realize symmetry differently have to be the same, then you might suspect that those two phases are somehow continuously connected, right? Just like the kind of low temperature and high temperature phase of Yang-Mills theory with quarks becomes continuously connected. And this idea, which goes back to the very early days of QCD, sometimes called Higgs confinement continuity, let me say a little more about it using an example that's even simpler than the one I was just mentioning. Let's imagine we just take an SU2 gauge theory, right? And we add to it a Higgs field in the fundamental representation of the gauge group. So this is a fundamental Higgs. This is enough in the Higgs phase to Higgs SU2 down to nothing. So let's imagine we study the phase diagram of the theory as a function of the Higgs mass squared. I'm imagining that there's a Higgs potential here, a quartic potential, gauge invariant. This is basically the standard model Higgs sector. This is SU2 gauge theory, but a fundamental doublet. And if I make the Higgs mass incredibly big, large and positive, much larger than the QCD scale of this non-abelian gauge theory, then I can integrate it out. And here I'm left with pure SU2 Yang-Mills, which is gapped, trivially gapped.
In this case, you do have a center symmetry.
Emergent. It's not exact, right? So when the Higgs mass is enormous, there is an emergent center symmetry, and it is unbroken in this gapped phase. But now I'm going to start dialing the Higgs mass and making it light. And the moment the Higgs mass becomes of order lambda QCD, the one-form symmetry is badly broken. Right? Because this thing is in the fundamental. So that's what I'm going to do. I'm now going to dial the Higgs mass down. This is the thing we did yesterday in the abelian Higgs model, right? And I told you that Coleman and Weinberg had solved this model and found that there was a first order transition. But we are not going to be able to solve the model in this range. In this range, the non-abelian strong coupling dynamics is operative. The Higgs mass is comparable to the QCD scale, so it's a strongly coupled soup. But we do know what happens when the Higgs mass is extremely big and negative, right? So when m Higgs squared is much, much less than minus lambda QCD squared, this is m Higgs squared much, much bigger than lambda squared. Here, we are again in a weakly coupled regime. We're deep in the Higgs phase. And then H gets a VEV. And Higgs is SU2 down to nothing. And so you again get a gapped and trivial theory.
Why do you say trivial? I mean, in the first case, you said there was an emergent symmetry. To classify the phase, you have to also take it.
No, but the problem is that even though in some sense the symmetry emerges, it's unbroken. So the symmetry doesn't act in any way in the infrared. The low energy effective theory in the infrared here is empty. There's no degrees of freedom. Yeah. Very much like what happened with the U1 magnetic in the Higgs phase of the abelian Higgs model. Okay. So this is the kind of simplest quintessential example of Higgs confinement. And so even though we don't know what happens in this regime, what we suspect based on the fact that these two phases look the same and the fact that there's no one-form symmetry that somehow lets us say anything, that in fact there is no phase transition in the middle here. So people believe that there's no phase transition. That this is also a smooth crossover. And this, of course, you cannot prove analytically. People have tried to study it on the lattice numerically, to the extent that I understand what was done. Some of this was done in the early days of lattice gauge theory, so it seems to hold up. Now, this model is not analytically tractable, but there are famous, rigorous analytic results due to Fradkin and Schenker, for example, and Banks and Rabinovich, that actually prove this in a whole class of lattice models. So they look at lattice models with gauge fields and matter in the fundamental, Higgs fields in the fundamental, and they show that you can identify in the phase diagram various corners that are demonstrably kind of weakly coupled Higgs phases or confining phases, and then they show that there's a kind of controlled region of the phase diagram where they can control the dynamics and show that there's no non-analyticity, right? So this is work that goes back to the 70s, to the early days of kind of confinement in QCD, and since then this principle has been kind of extremely widespread. It's also been checked and observed in many, many analytically controlled models, for example, models with supersymmetry. If you know a little bit about supersymmetry, you know that they're typically moduli spaces of vacua, which are parametrized by scalar Higgs fields. And those scalar Higgs fields let you kind of continuously interpolate from one regime to the other. And because of supersymmetry, you can control what happens in between. So you can actually do this interpolation and see that there's no phase transition. All right. So this is the sort of standard picture of what happens when you don't have a one-form symmetry, right? And this is in total agreement with the kind of Landau point of view on phases and symmetry breaking, right? Just like in the phase diagram of water or in the Ising model, if you have the Z2 symmetry, then there is a sharp transition. If you explicitly break the Z2 symmetry, you can go around the transition. So this is supposed to be an example like that. And as I said, this is not just kind of empty reasoning. There are tons and tons of examples where this is actually true. So this is sort of the standard scenario. Any questions about this?
Yeah. Sorry, what does it say on the blackboard over there? Is it SU2 plus again?
Oh, well, I just said we're going to do the same step again. So we're going to add another Higgs field.
So the situation SOU3 is the same. If there is a Higgs confining continuity.
Sorry?
The situation there is the same as in SU2?
In-
SU3?
In SU3? Yeah. If you add two Higgses, I think it's believed to be the same, yeah. So, you have to make sure when you add Higgs fields, you have to make, and you do it in a way that's too elementary, you might have some global symmetries carried by the Higgs field, so you have to make sure that you add a potential and maybe some other interactions that are sufficiently generic that you don't have any global symmetries. Actually, this model does have a global symmetry. If you know your standard model, there's a custodial SU2 that acts on the Higgses. But the custodial SU2 is actually unbroken in both asymptotic regimes. In the confining phase, it's obvious. And in the Higgs phase, it's unbroken because of color flavor locking.
So that SU2 doesn't make an appearance here.
But this doesn't break your argument, maybe like it's restored in the middle?
No, it's unbroken everywhere.
Oh, so.
So to connect to the discussion yesterday, any discussion of two-group symmetries for no abelian cases and no body size for the phases? Any discussion of the two-group symmetry?
Well, in order to have two-group symmetry, you at first need to have a one-form symmetry. So in Yang-Mills, there are Yang-Mills theories with one-form symmetry that also have two-group symmetry. Not SUN.
Like SO?
SO,
I see.
things like that, with certain matter.
What are the implications of the two-group symmetry? Well, okay, I see. Just pure Yang-Mills, so
Well, it doesn't need to be pure. It could be Yang-Mills with for example, SO with vector quarks for certain numbers of quarks has this. Yep.
Okay.
All right. So what I want to do in the remaining time is at least sketch some examples for you where situations that superficially look like this, that superficially look like theories without one-form symmetries, where the Higgs and the confining phase are indistinguishable, can actually be distinguished, and you can prove that there has to be a phase transition. But the thing that distinguishes them is not a one-form symmetry. Remember, the whole starting point for this discussion was that QCD, with either fundamental quarks or fundamental Higgs fields, does not have a one-form symmetry. So you have to use some other symmetry, but QCD has lots of symmetries. And the thing that will distinguish them is not whether or not a symmetry is broken, because after all, these two phases are gapped and trivial, but it will turn out to be closely related to what you've been hearing about from Max, which is that there will be non-trivial invertible phases for the symmetry that are different in the Higgs phase and the confining phase. So this does not happen in this simple model. The simple model, to my knowledge, really has continuity, but it does happen in other models that have both Higgs fields and fermions, and in particular it happens in actual real-world QCD if you put the theory at finite density. So I probably won't have time to discuss finite density QCD, but I'll try to sketch you at least one or two toy models with scalars and with Higgs fields that naively fall into this continuity class of models, but in fact have a phase transition because a non-trivial invertible phase appears on one side of the transition while the other side remains trivial. All right. Any questions before we move on to that topic?
So for the Higgs phase, there is still GNN symmetry?
No.
Why? How is it different?
Well, the Higgs field explicitly breaks it. The model doesn't have it from the get-go. Yeah, the only place where it emerges is over here. All right, so in order to talk about that, I'm going to need to know something about the invertible phases of fermions in 4 dimensions, in 3+1 dimensions. You've been hearing in Max's lectures about invertible phases of fermions in 1+1 dimensions. And we'll need a small generalization to 3+1 dimension. It turns out that the generalization actually involves fairly elementary concepts. So we won't need to develop too much technology. So before we get to QCD with matter fields, let's just discuss free fermions. So let's take a single two-component Weyl fermion in 4 dimensions. That's, if you are into these things, equivalent to a Majorana fermion in 4 dimensions. I'm going to use the Weyl basis. So this is a 2-component spinor index, and psi is complex. And this is the Lagrangian. This is just a free fermion. So this is a nearly immediate generalization of the free Majorana that you saw in 1 + 1D yesterday. Now, in general, M is complex. But if you allow M to be complex, it turns out that you break time reversal symmetry. And without time reversal symmetry, there are no interesting non-trivial invertible phases for free fermions in 3 + 1 dimensions. So that's different from the 2-dimensional case where the Kitaev chain is already non-trivial. If you just have fermion number, then it becomes even more non-trivial when you throw in time reversal symmetry, as you saw in the homework, I think. In 4 dimensions, we actually need to insist on time reversal symmetry in order to have a interesting non-trivial SPT. So let's insist on T symmetry. That's something that you're certainly entitled to do if you study this model. Then it enforces the reality of the mass in this convention. This is a T symmetry that has the property that it squares to -1 to the f. Now, depending on what we're going to apply this to, assuming T symmetry may or may not be a good idea. Of course, T symmetry is badly broken in the standard model, for instance. But in QCD, it's an excellent symmetry. 10 to the -10 excellent. Lots of people trying to figure out why it's so excellent. But it is a fact that it is a symmetry, and so we can use it. So once you insist on time reversal symmetry, then the mass is real, right? And now you have phase diagrams that are similar to the ones that you saw yesterday from Max. So you can study the phase diagram as a function of the mass. And of course, at the massless point, you get a free massless Majorana, or Weyl, and here the theory is gapped. Gapped here and gapped here. And in fact, there is even a symmetry that flips the sign of the mass. This model has an axial symmetry, U1 axial, that rotates psi by a phase. Remember, psi is complex. And this U1 axial rotates M by a phase. So if you rotate M by pi, you can relate the M and -M phases. So that means that superficially, until you ask more sophisticated questions, these two phases are actually identical. We have gapped, gapped, and moreover, related by the axial symmetry.
All right.
So for the Weyl fermion, is the mass term more important?
Of course.
Just Weyl fermion, not the George fermion.
Yes.
Otherwise, I would not have written it down. This is the Dirac mass term, or half of the Dirac mass term.
In fact, you just proved that without the time reversal, there is just a single phase.
Correct. Yes, excellent. So if you make M complex, you get the whole complex plane, and you can go around this point as many times as you want, and it all looks the same. And in fact, the action of this U1 axial is precisely to do this. Now, what do you need to do in order to see that these two phases are subtly different in the presence of time reversal? You need to study, as you learned yesterday, the problem on non-trivial space-time manifolds, non-trivial Euclidean space-time geometries. So for the model yesterday, a torus was good enough. And here it turns out that you need something more sophisticated, maybe like a K3 surface, which is not so natural in condensed matter. But It's okay in string theory. All right, so let's turn on a background metric. So we're studying this problem now on a Riemannian form manifold M equipped with a background metric G. And then, well, remember yesterday we discussed triangle anomalies for U1 symmetries. Here, in this model, we have a triangle anomaly involving the U1 axial, and there's the fermion loop, and then there are two stress tensors, or two gravitons, if you wish. Right? That triangle anomaly is non-zero, and it tells you that the divergence of the axial current is proportional to trace R wedge R, the Pontryagin density for the gravitational field. So what this tells you is that if you use the U1 axial symmetry to take m to minus m to rotate the phase of the mass by pi, then you generate a non-trivial theta term for the background metric. So what you learn is that at low energies, the low energy effective action as a function of the background field, the background metric, is up to continuous counter terms that we're throwing out. A term that looks like a gravitational theta angle. Here R is the Riemann curvature of the metric, and I am putting conventions here such that on spin manifolds this angle theta g is 2 pi periodic. Why do we need spin manifolds? Because we have a fermion in the game, so we need a spin structure. All right, and so what happens is that the axial anomaly tells you unambiguously that if you flip the sign of the mass, this theta angle jumps by pi. What the axial anomaly does not tell you is which of the two phases corresponds to theta equals 0 and which corresponds to theta equals pi. That's a choice. It's a choice of scheme. That discussion already came up yesterday. If you're on the lattice, then in principle there's a microscopic choice of scheme that you put in, but in the continuum there's no such thing. The choice of scheme is just up to you, and you can pick it arbitrarily. So I'm going to pick a choice of scheme in which theta g is 0 for positive mass, and theta g is pi for negative mass. Why?
Would it be that both phases have non-zero theta g? Different by pi, but both non-zero.
Well, so
pi over 4 and 3 pi over 4.
So I was going to say that next. The only values of theta g that are consistent with time reversal are 0 and pi. Yeah. If you don't have time reversal, of course, you can move theta g around arbitrarily and the whole thing falls apart. But because we insist on time reversal, this theta g, which is a 2 pi periodic quantity, gets pinned to 0 and pi. It becomes a quantized quantity rather than a continuous one. And theta equals 0 is the trivial phase, theta equals pi is the non-trivial phase. All right. So this is the gadget that we're going to use to try to explore Higgs phases and confining phases of QCD-like theories. And in particular, the general logic of invertible phases tells you that if you have two different phases in which theta g takes different values, then no matter how complicated the theory and no matter how little you know about the dynamics, there has to be a phase transition in between. Of course, in this model, it's super simple, because the phase transition is just the gapless point for the fermion, so it's second order. But it doesn't need to be. It's trivial to soup up this model to make the transition first order. And in general, you simply don't know what the order of the transition is. In fact, you don't even know that there's a single transition. There might be multiple transitions. Any questions?
I understand that because of the transition and m equals to 0, typically you do not expect that theta g is the same at m equals bigger than 0 and m is smaller than 0. But should you expect some kind of continuity? Do you expect some kind of continuity of theta? Maybe I should rephrase the question. Can you choose theta g to be 0 all over m?
No. I could not. The jump in theta at across m equals 0 is completely unambiguous. It's fixed by the anomaly. It's fixed by the fact that we have one fermion. If we had two fermions, then each of them would make theta g jump, and then the two phases would be the same. Then we would get theta g equals 0 here and theta g equals 0 here. But if we have an odd number of fermions that jumps, the anomaly unambiguously tells us that theta g has to jump. That's because this triangle anomaly counts the number of Weyl fermions. This is just proportional to the number of Weyl fermions.
Yeah, but that's the physical meaning of anomaly. It's just this, it doesn't couple to fermions themselves. So
What?
no, this term doesn't.
No, but the metric couples to the fermions.
This term arises from integrating out fermions with different signs. This theta angle arises from the determinant of the Dirac operator for this fermion, the phase of the determinant of the Dirac operator. Very good. So let's.
If I may mention, Max's arguments were solid. He was like saying, look, here we have some edge states, here we don't have edge states, here the number of edge states changes.
There are also edge states here. Yeah. So this example of an invertible phase is called a topological superconductor. And the corresponding edge states have fractional gravitational transimmons term, fractional thermal Hall conductivity. In the simplest case, there's a free Majorana edge state. There could also be topological order. So this type of invertible phase is very much in the same class that he was discussing, with all the same nice features.
Do we ever need to go to curved manifold, or can we just stay in the flat space and just stay on the boundary?
No, and indeed, in condensed matter, yeah, but so you need one of the ways you can look for this is to look at the boundary, exactly. And indeed, you cannot put a non-relativistic model. In order to activate this, right, you need a manifold where this is non-zero. So as I said, K3 will do the job, but you cannot put a non-relativistic theory or a lattice system on K3.
But these are two very different things conceptually, right? Is there any guarantee that whatever you can detect on some crazy manifold, it can be realized on flat space in some crazy boundary condition?
Well,
I don't know. Maybe you want to answer?
That's the belief.
That's a belief.
All invertible, non-trivial invertible phases have non-trivial, have boundaries with optimal.
Yeah. Although,
My definition of anomaly.
Okay. We're confused about an example on Monday,
but of course, here I'm in a fully relativistic setting, so I can do both, right? I can go both on the manifold and look at the boundary, right? But this thing is very, but you know, this notion of an invertible phase is very robust. So, for example, I told you before that one of the things you can do is you can take QCD and put it at finite density, at finite chemical potential. That breaks Lorentz invariance. That system cannot be put on K3, but you can still look for these things.
But by boundary, you mean boundary between theta equals between negative m and positive m.
For instance, you can think of positive m as a kind of trivial reference state. So you just like what Max was saying yesterday, you can think of positive m as vacuum. At some point, you need to define what you mean by vacuum, by like the trivial state, and that's a choice of scheme. That's a choice of counterterms that you need to make once and for all. So you might as well pick a scheme in which the positive m state is the trivial state, and then a boundary means a domain wall between positive and negative m, which in this free fermion model would have a single Majorana edge mode on the boundary, a 2+1 dimensional Majorana edge mode on the boundary. Okay, so let me sketch in the last 15 minutes or so how you can soup up this model to make the Higgs phase and the confining phase distinct, and they're distinct by precisely this gravitational theta angle. So, clearly, based on where I was going with this, I mean, this is an effect that is due to fermions, and so therefore I need to somehow take this bosonic system and add fermions. So let me add fermionic quarks to this model. This is an SU2 gauge theory, so you might know that there's a gauge anomaly unless you add an even number of fundamental fermions. Right? You can't add an odd number of fundamental fermions. So let's take two fundamentals of SU2, so two SU2 doublets. And let me give them different indices. Let me take A to be a fundamental gauge index. And let me take I to be a kind of flavor index that labels the two quarks. And in fact, what I can also do is I can add this flavor index to my Higgs field from over there. Remember, there I just said that we have a complex Higgs field in the fundamental of SU2, but you might know from the standard model that you can think of the complex Higgs field of SU2 as a real bifundamental of SU2 gauge and SU2 custodio. So this model has an SU2 gauge symmetry, and it has an SU2 flavor symmetry, which in the standard model is called custodio. Let me just call it flavor. The flavor is not going to be so important in what I say. You can also keep track of it. It turns out that there are also theta angles for flavor symmetry, and you can keep track of them as well, and they'll also give you interesting information about the phases. But let me not do that. We'll just get to the very simplest example. And then if I have time, I'll say a little bit more about kind of more physical examples. All right, so these are the Higgs fields that we're adding to our theory. And now what I want to do is I want to couple the Higgs fields and the fermions into this model. So the Higgs fields are already there with their potential, right? There's a Yang-Mills term, there's a kinetic term for the fermions. What I want to do now is to add a non-trivial coupling between the Higgs fields and the fermions. All right, so the total Lagrangian of this model is L Yang-Mills plus some kind of fermion kinetic term. Let me schematically write it like that. Then there's a Higgs kinetic term. Then there's a Higgs potential. And then there are Yukawas. And the Yukawas look like this, up to factors. There are two different combinations of Yukawas. Let me call them Y1 and Y2. One is HA, HB, IJ, psi, I, psi, PJ. Right. When you contract the fermions into a Lorentz singlet, right, they have two gauge indices and two flavor indices, and you certainly need to contract the gauge indices to make something gauge invariant. I'm also choosing to preserve the flavor symmetry, although that's up to you whether you do that or not. So it turns out there are two ways of contracting these indices, and that gives you the two Yukawas.
Are we in 4D?
What should I draw?
Inside the.
Oh, I'm sorry. You're right. I should have dropped them. Thank you.
Yeah, we're in 4D.
So this is relevant.
Yeah, but it will turn out to be dangerously irrelevant. And you'll see that in a second. So this is a dimension 5 operator. And in fact, again, if you take the analogy with the standard model seriously, these are the analog of the Weinberg operators in the standard model. So these are the dimension 5 operators that give you principal neutrino masses. But of course, in the standard model, this part of the electroweak sector has no time reversal symmetry. I'm going to insist on time reversal. And time reversal implies that Y1 and Y2 have to be real, just like my mass over there had to be real. So indeed, this is a non-renormalizable model, and you can have lots of complaints about it if you want to take this model seriously. I just want to use it as a toy model to illustrate how you can engineer an SPT jump. There are renormalizable UV complete models that do the same thing. The reason it doesn't work in this model is because we're doing these pseudo-real representations of SU2, so you need at least 2 Higgs fields to make something gauge invariant. So just imagine that I've fine-tuned my model so that all the higher irrelevant operators are tiny, and this is the only one that gives you the leading effect. This is just a point of principle. And in principle, you can choose these y's to have different signs. The sign of the y's actually matter. Let me for fun just do the case when they're positive. All right. So this is the model. And now I'm going to repeat my discussion from up there. Remember the discussion up there was I was just dialing the Higgs mass from very large positive masses to very large negative masses. This is the interpolation between confinement and Higgsing. And now we're going to see what the effect of this term is. So in the very large positive mass phase, of course, nothing changes. Right? Let me draw the same phase diagram. Here's 0. So when we're way over here, I can again integrate out the Higgs field. It just disappears from the theory. Then when you integrate out the Higgs field, you generate very irrelevant multi-fermion operators. You get SU2 gauge theory with 2 quarks and these very irrelevant multi-fermion operators, which basically means that you flow to normal QCD. And so this gives you a confining gapped, well, let me not call it confining since there's no one-form symmetry, gapped theory, trivially gapped. It turns out that the SU2 custodial is unbroken, but let me not say more about it. All right. I should maybe say that just to keep on the safe side, I'll also add quark masses so that we don't have to worry about any chiral symmetry breaking. I think I said that somewhere in the beginning, but let me say it again. Right? Otherwise, you might worry about something like chiral symmetry breaking here, but I'm just going to stay at positive quark masses. The quark masses are not what drives the story here. The thing that drives the story is the Yukawas. So you know that you see that the Yukawas are totally irrelevant in this positive mass phase. So let's now examine what happens in the negative mass phase. Right? So when we're all the way over here, then we're in the Higgs phase. And if you have a doublet like HI that gets a VEV, right, and you think of it as I have done here as a bifundamental of SU2 gauge and SU2 custodial, then that means that H gets a VEV that locks its color and its flavor indices. All right. So this is sometimes called color flavor locking. It means that it has the consequence that the SU2 gauge is completely broken, but the SU2 flavor is unbroken. Basically because this diagonal mixing allows you to compensate the superficially broken SU2 flavor symmetry with a broken gauge symmetry, and you actually have that symmetry. So that means that there's an unbroken SU2 symmetry under which I can decompose all my matter if I want to. Right? So let me do that for the quarks. The quarks are also bifundamentals of SU2 gauge and SU2 flavor, right? So they're sort of 2x2 quarks. And when you decompose them under this diagonal color flavor locked SU2, they decompose into a singlet and a triplet. Right, so the singlet is the trace, and the rest is the triplet. Now, you see that these two Yukawa couplings have different tensor structures in the color and the flavor indices, right? So they respond differently to the two SU2 representations. The trace is easy. You can just plug in delta ij into this, and you get the mass for the singlet. And then you have to do something else to compute the mass for the traceless triplet, right? And so what you find is that the singlet and the triplet get different masses. And in particular, the triplet masses look something schematically like the quark mass minus the VEV, And the singlet mass looks something like the quark mass plus the VEF, with some factors of 2.5 that I've been ignoring.
That's squared.
Or, I don't know, why VEF squared?
Well, because you have Higgs centers twice into the quark cluster.
You're right. And also there's a y, which is dimensionful. So roughly speaking, y v squared, y v squared. Yeah. So you see that the sign of v doesn't matter, but the sign of y does matter for this. To pick the y's to have different signs, you actually get different masses. So with this particular choice of masses, with positive y's, I see that if the VEV is enormous, so that I'm deep in the Higgs phase, where I can do weak coupling analysis, then the triplet of SU2 custodial flips sign, and the singlet does not. Right? And from what I told you over here, every single two-component Weyl Fermi on that flip sign triggers a jump by pi and theta. So you start with theta equals 0, and then you jump an odd number of times, 3 times, and then you land at theta equals pi. So what we conclude from this is that in this trivially gapped phase, theta was conventionally set to 0, and in this Higgs phase, theta g equals pi. Turns out there's also a theta g for the SU2 custodial. So what this shows is that even though this regime is just as strongly coupled as it was before, and we know as little about it as we did before, we can now conclude unambiguously that there has to be a non-trivial phase transition somewhere in between. Just by virtue of the fact that theta g jumps by pi. All right.
If you cover the negative, it's the same thing.
Well, you have 2 Yukawas, and so you have 4 different choices of signs. For some choices of signs, they're the same. And for some choices of signs, they flip. So you have to check all the cases. Yeah, in this model, you can engineer any flip you want. All right. So I don't have time to show you other models. This is the simplest model. That is a sort of direct generalization of this SU2 example. But it turns out that you can do the same thing with models that are SU3 gauge theories with kind of QCD-like quarks and Higgs fields. And it turns out that you can do the same thing with honest-to-God real QCD without any extra bells and whistles if you go to finite density. And in particular, if you study 3-flavor QCD at asymptotically high densities, it is also in a color flavor locked phase, and it also has theta g equals to pi. So that means that in all of those settings, there is now a kind of new reason to expect a phase transition that wasn't there before, because there wasn't a one-form symmetry to make you believe that there should be. And I think it's interesting to try to understand where that could be and what could be the consequences. So let me stop here maybe and take some questions.
Does this transition falls into Landau paradigms?
No.
No.
Does not.
Right. So I mean, if by Landau paradigm, even in the generalized sense, you mean that the phases are characterized by whether or not some kind of symmetry is broken and unbroken. It could be a normal symmetry, it could be a higher form symmetry, but it has to be broken and unbroken in the 2 phases. Here we have a symmetry, which is important, which is time reversal, but it's unbroken everywhere. And the thing that is signaling the phase transition is not whether or not something is broken, it's whether or not you have a non-trivial invertible phase or a trivial invertible phase. So I would say that all of these invertible phases go beyond the Landau paradigm.
I don't know if that's a universally shared opinion.
So earlier you said something about one-form symmetry generically is broken at high temperatures and restored at low temperatures. But say for like Zn gauge theory, I guess it's again the opposite.
Well, do you mean Zn gauge theory in the continuum or on the lattice? They're very different. With or without monopoles.
I guess I was thinking of the lattice.
Yeah. On the lattice, it'll behave, I think, somewhat similarly. In the continuum, it's a DQFT, so it doesn't do anything as a function of temperature.
The end gauge theory on the lattice doesn't says the symmetry is not restored at high temperature.
The one-form symmetry?
Yes.
The one-form symmetry should be broken at high temperature, right? That's what I would expect. Other question? Yeah.
What symmetry are you using in QCD? Real QCD?
Time reversal.
So there you also get a. Where's the time? If you slightly break time reversal, do you completely lose any ability to say if it's a phase transition?
I don't think you completely lose the validity. I mean, time reversal is presumably broken by a very tiny amount if you take into account standard model corrections and so forth. The fact that, but I mean, I don't.
I mean, in your free fermion model, as soon as you let go of time reversal, you do lose the phase transition.
Well, but I mean, then we have to get into a discussion about what it means to break time reversal strongly, weakly, by a small amount, by a large amount. If you allow me to only break it by a quote unquote small amount, I don't know what small means since this is the only scale in the problem. But roughly speaking, if you break it by a very small amount, it somehow means you go very close to this transition. So you might be like arbitrarily close to the critical point.
But can you argue that this transition persists? So presumably you're at low temperature.
Yeah, I'm at zero temperature.
Zero temperature. Can you argue that it persists for some finite amount of temperature?
I'm not sure about that. That's an interesting point. So generally speaking, these like SPT induced transitions are really zero temperature transitions, and some of them are very fragile to turning on finite temperature. And in particular, if you take the free fermion examples, right, putting finite temperature immediately gaps the edge modes. But there are interacting examples that have been found to be more robust. So maybe the transition could persist to small temperatures and then disappear. I think it's a dynamical question. It's not, but in general, the SPT disappears once you turn on finite temperature. Yeah. And in fact, that's necessary in order for me to kind of avoid a conflict with the statement that as a function of temperature, QCD doesn't have a phase transition. Yeah.
Can I have something similar, but instead of using this gravitational anomaly, I use the background for the vectorial field, for the vectorial symmetry?
Yeah, I think I saw that multiple times. So there's this SU2 flavor symmetry, this custodial symmetry, and if you also keep track of the theta angle for that, you'll find that it also jumps.
Oh, okay, but I won't say this, but also in the context of the super simple example of the free fermion.
The free fermion doesn't have a vectorial symmetry. It's one fermion. It's one Weil fermion.
Oh, okay.
So it just has a chiral U1 symmetry, which is a kind of axial symmetry. Yeah. Right, but in QCD you could keep track of baryon number or the SU3 flavor symmetry, the kind of diagonal SU3, the Gell-Mann SU3 flavor symmetry, and that also jumps.
Okay, and for example, in the example of free fermion in 3D, 3D. In 3D, in that case, I expect to have a jump in the Church-Simons.
Correct.
Okay, thank you.
That's actually a much more conventional setting where people use jumps in Chern-Simons term to diagnose phase transition. If you wish, that's also an example of this invertible phase business. Yeah, but it's more standard.
Yeah. You emphasize this the Higgs phase and confined phase are really can be connected smoothly. Yeah, I think there's a result as the continuous transition of a Higgs transition and the peak time transition cannot be connected smoothly using the similar argument. The one is controlled by magnetic symmetry, the other is controlled by electric symmetry, electric one-form symmetry.
Well, I think we had this discussion a few months ago. Maybe I think the model you're referring to is the Fradkin-Schenker model, right?
Yeah, that's right.
Right. So the model that was originally studied by Fratkin and Schenker is a Z2 gauge theory on the lattice with a fundamental Higgs field, and it has two couplings. So it has a two-dimensional phase diagram, and the phase diagram looks something like this. And roughly speaking, here you have Higgsing, where something electric condenses, and here you have confinement, where something magnetic condenses. The model has an electric-magnetic symmetry around the diagonal. And so what Fratkin and Schenker showed completely rigorously, and also is confirmed by lattice simulation, is that you can avoid the phase transition here. What I think you're talking about is this region.
If transition line is continuous, then because using this thing, this one-form symmetry, electric-magnetic.
Here, this is deconfined.
But along the transition line,
Here.
Yeah, this transition line.
These are not smooth. These are Ising star. Yeah, these are interesting second-order transitions, and this is a first-order line.
But I try to say there's a one using the same argument that you using the one-form symmetry you just explained here. These two Ising stars are different transitions.
That's right. They're kind of mutually non-local.
Yeah.
I agree.
But what I want to emphasize is the fact that this transition has to be there, you can see without knowing anything sophisticated about symmetry, simply because there's a deconfined Z2 here, right? And there's nothing here. So.
And but I wonder, this is a two-dimensional. I don't know, in 3 plus 1 dimension. In 3 plus 1D, those usually those transitions are first order.
People have done this.
But however, can you zoom into the second order transition boundary and one may have similar results?
So people have actually done this, like Tin Suleiman Pasic and his collaborators, for example, have simulated exactly this kind of setup in 3 plus 1 dimensions, and they get like first order lines everywhere. There's no second order. Like all of these, in 3 plus 1 dimensions, all of these lines are first order.
Yeah, but the second order must be multi-critical. So.
Well, okay, so maybe one can find a multi-critical point. Yeah, that I don't know. Mm-hmm. Right.
Let's thank Tom.
Thanks.
Again.